Hi everyone, today I want to talk about something very important in electronics that many people don't think about. Jitter. Have you ever had a phone call break up or your fast internet suddenly lag? This issue often comes from jitter. Jitter is a small timing variation in signals. Even though it's small, it can have a big impact on how well your system works. If we don't understand jitter, we might run into problems we cannot easily explain. That's why learning about jitter is so important for all of us working with circuits. Let's start with ADCs, or analog to digital converters. Think of trying to take a photo of a moving object. If your hand shakes a little, the photo comes out blurry. That's what jitter does in ADCs. It adds shake to the timing. The converter samples the signal at exact time, and jitter messes up the timing. Even a tiny timing mistake, called absolute jitter, can make the result less clear. For example, in medical imaging, jitter can blur the capture data. When we reduce jitter, the digital data looks more like the real signal. That means better medical images, better sound quality, and better results in many applications. Now, let's talk about DAC, digital to analog converters. This works the other way around. They turn digital signal into analog ones. Think of someone playing a piano, and the timing of each note is just a little bit off. It doesn't sound right. That's jitter in a DAC. It changes when signal is created, and that can cause poor sound or inaccurate output. For example, in high-end audio or test equipment, jitter can ruin performance. So, reducing jitter helps you get smooth and accurate analog output. For digital systems, clock timing is everything. Think of dancer move in sync with music. If the music speed changes randomly, the dancer gets confused. That's how jitter affects digital circuits. Two main types here are pure jitter or cycle-to-cycle jitter. Pure jitter is when each clock cycle changes a little. Cycle-to-cycle jitter is when the timing between two back-and-back cycle changes. Both can lead to the missing data or logic error. For example, an FPGA doing signal processing can give wrong result if the timing isn't steady. So, keeping the clock stable means better performance and fewer errors. Let's move on to the PLs, phase lock loops. These keep timing steady in system, like a conductor keeping an orchestra in sync. But noise or interference can still sneak in. Random jitter happens from things like thermal noise, like static on a radio. Determinist jitter happens from regular noise like power supply ripple. If the PL is fitting a fast processor, even small timing change can cause big problem. Reducing jitter in PL keeps your system running on time and working correctly. In RF and wireless systems, jitter show up as a phase noise. That's like hearing a radio signal that wobbles a bit. If the signal shifts even a little, your audio or data can get messy. Think of a drone using GPS. If timing is off even slightly, its position could be wrong. That's how serious jitter can be. But managing jitter, we can clear signal, better calls, and more stable wireless connections. In wireline communications, that SerDes, jitter is also a big issue. This system sends data really fast. Imagine you are sending pulse through a channel, but your hand is shaky. That's jitter. The pulses doesn't land exactly where they should. Over time, that small error grows, especially with determined jitter in data center or high-speed networks. This can cause data errors. If we keep jitter low, we can move data faster and more reliable. Now, for memory interfaces like DDR, these systems work like traffic light managing cars. The timing has to be just right. Duty cycle distortion over DCD is a kind of jitter that messes up the spacing between clock edges. That's like a traffic light turning green too soon or too late. If the timing is off, memory access can slow down or give bad data. Good jitter control means faster, more reliable memory systems. Some engineers might think it's okay to ignore jitter at first, but that can lead to big problems later. It's like building a tall building without checking for small shakes. Sooner or later, it could collapse. Jitter problems can cause system crashes, bugs that are hard to fix, or even a total redesign. That's expensive and stressful. If we work on jitter early, we avoid all the trouble. Learning about jitter is one of the best things you can do as an engineer. Engineers who know how to deal with jitter are more vulnerable to their teams. They help create stronger, more reliable systems, and that means better products and better careers. Here are summarized images showing you why you need to continuously exploring jitter in your specific applications, such as ADC, DAC, PL, digital clocking, RF, optical communications, or memory interfaces. Discuss these insights with your peers, mentors, and industry experts. Commit today to mastering jitter. Your future projects, career success, and personal reputation depends on it. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video with the people who may be benefiting from it.